To the first of our pre-class videos. So in these videos what we're going to try to do is to explain the essential content of it without many examples, so that we're not cluttered with all these examples, but rather just giving the essential components of what we're doing. And then in class I'll just do lots of examples and answer lots of questions. Alright, these are probably good for reviewing even if you don't necessarily watch them before the class. Alright. So the first thing we do is the syntax. So the comments, first thing to do is the comments. Comments are either dash dash followed by a comment to the end of the line, or they're within this angle bracket like this, and this angle bracket like this can actually be anywhere, and it can include multiple lines. So there are two ways of doing comments. So variables are either prefix made up of letters, digits, this quote, so x and x quote can be both different variables, or the underscore and starts with a lowercase letter. So that's what the variables are. Or they can be infixed, made up of sequences of other characters. So we can have arbitrary other characters can make up as a variable. In Haskell, the indentation is significant. It's not as strict as Python, for example. As long as it just keeps indenting more, then you can see it as including what came before. Parentheses are used for precedents and tuples. They're not for the arguments of functions. And in particular, comma is an infix variable, so it has a value to it. And function application binds most strongly. So factorial 3 times 5 means factorial 3 times 5. So you're always going to carry out the prefix variables before you carry out the infix variables. So they bind the most strongly. And we can swap between them. So binary prefix functions can be made infix using a back quote. So div is a function that takes two arguments, and you can make it infix by putting quote div quote, and this is a back quote. And infix operators can be made using prefix by putting them in parentheses. Okay, so you can mix them up. So you can have infix and prefix. So equality special, it provides definition. So x equals 7 provides a definition of x. And we can define functions. So this name followed by all the arguments is e, where x1 to x2, these xk are these formal parameters, and e is an expression. So this name here takes k arguments. Okay. So these arguments can contain constants and structures, but each variable in it can only appear once. So we're allowed to have constants and structures. We're allowed to define them with constants and structures, and each variable only appears once. Multiple equations can define a function. The first one to succeed is used. Okay, so within a definition of a name, the order matters, but we can define different variables can have differently defined arbitrarily. So they're all just definitions. Okay. Haskell evaluates expressions. So Haskell knows how to implement some of these, like says 3 plus 4 times 7. So it's going to multiply 4 by 7 just using a normal precedence and add 3 to it. So it gives you 31, I think. Okay. Now, given this definition of a name, so name of x1 to xk is equal to e, then the expression, when I write the expression, I have k arguments, where all of these k arguments are provided. It evaluates to the expression of e, but with x1 replaced by v1, x2 replaced by v2, and xk replaced by vk. So that's what we're going to do. We're going to do, when we see name with all of these k arguments, we're just going to evaluate e, but replace x1 with v1, x2 with v2, and xk with vk. Okay, and basically that's all there is. So we have x times y plus 100 with x replaced by 9 and y replaced by 3 evaluates to 9 times 1000 plus 3, which is 9003. Okay, that's basically all there is in Haskell. That's how it works. So as an example of doing this, so foo of xy is equal to 1000 times x plus y, then foo of 3, right? What happens is that foo of 3, we have this, we're going to evaluate this, but with x replaced by 9 and y replaced by 3. Right? If we say bar of foo 7, well, this just provides a definition of bar. Okay, it doesn't do anything. It doesn't evaluate foo or anything. It just defines a definition of bar. So if I write bar of 3, well, bar is foo of 7, so that's exactly the same as writing foo 7,3, which is 7,003. Okay, so that's what's going on there. Hope that makes sense. Try it, type it in, and see what happens. Okay. Now, the other part of Haskell is the types. So function definition of name x1, x2 to x is k can have this type declaration. So it can say t1 is a function from t1 into t2 into tk into t. And these pair off. So each ti, alright, so this one here is the type of the first argument. So this one here sort of says that this name here, the first argument has to be of type t1. The second argument has to be of type t2. So when we're evaluating this expression, that expression has to be the right value. So ti has to be the type of the first argument, t2 is the type of the second argument. And t is the type of this expression here. Okay? In some sense, a nice way of thinking about it is each function only takes one argument. So if you apply name of v1, that's a function of type t2 into the tk. So if you assign t1, it's a function of all the rest of these. Okay, and v1 has to be of type t1. Okay, now if you assign all of them, if you assign all of these, it's a value of type t. Okay, and the value is the value of e with each xy replaced by this vi. So when we assign all of them, we end up with the value of e, but with each xi replaced with vi. Okay, so let's have a look at some particular types we're going to do. So here are the types that we're going to look at. We're going to look at booleans, we're going to look at numbers, we're going to look at equality, characters, and strings. Okay, so we're actually going to look at characters and strings next time. But these are the basic types. So bool is a type with two values, true and false, and their operations are and, or, and not. So in class we'll actually have a look and see about how to actually go about how you could actually define and, or, and not. Okay, and then we could think about how we could define exclusive or. So think about how to go about doing that. Turns out you can also define if then else. So think about how you might define if then else in Haskell with only knowing what you already know. You can define if then else. And if you think about also what happens if you try to do this in another language like Java, what happens if you try to define if then else just within Java? Just think about what happens. Alright, so the other type is integral types that represent integers, and they implement plus times power, which is this up arrow, which is this up caret, minus div mod, the absolute value, and negate. Turns out there are two implementations of this, of integral. There is the fixed precision integers, which is the same type we get in, the same normal type that we get in Java or C. But there's also arbitrary precision integers that can have precision can be as big as the amount of memory you have in your computer. So you can have billions or trillions of significant digits. Okay. Integral is a class. So integral here is a class. In these two implementations, int and integer are types in this class integral. And only types have implementations. So in some sense you can think of Haskell classes are like Java interfaces. So they define what is in them. So define here's what this type is. This class integral has types inside it, and each element of the class integral implements all of these operations. Okay, so here's an example of this definition. So here's the definition of div. So div is a function that takes two arguments of the same type. So this is the first argument has to be the same type as the second argument, and returns a value of that type. Okay, that's what we just saw before. That's what this means. This is a function of that takes something of type A and something else of type A and returns something of type A. Okay, and now this type A is going to be a type in this type definition, but type has to be in the integral class. That's what this means. This means that it's a function from that div takes two arguments of the same type and returns the value of that type, and the type must be in the integral class. Okay, fractional types represent real numbers. So the previous was integers. They implement plus, times, caret is power, minus, and these were all implemented. Remember, these were all for integral classes as well. Slash is divide, so it's a fractional divide, the absolute value, and negate. Floating types are also fractional, but also implement log, sine, exponent. And there are multiple implementations, and each of these implementations is a type. So, for example, there's double precision floating point numbers, like in C and Java. Okay, they're double precision floating numbers. There's also float. There's single precision floating point numbers. Don't use these. They're not very accurate. But there's other ones. There's exact rational numbers. There's another implementation of fractional. Now, rational is interesting because it's in fractional, but it's not in floating. So log, sine, exponent are not defined for rational, but they're defined for doubles and for floats. So it turns out there are no types that are both integral and fractional. You might get tricked out sometimes because Haskell doesn't know that there are no types that are both integral and fractional. In fact, it's possible to design some of these types that are both integral and fractional, but we don't tend to, they're not very useful. So what we do is there's also a generalization of these. So these are the ones that are in common between fractional and integral as plus, times, power, minus, absolute, negate. So this is wrong. So divide should not be in there. Whoops. So num is a class, and the elements of those types, and integral and fractional are both subclasses of num. Okay. So equality types. So EQ is another class. And EQ types implement equal and not equal. So that's the only things in the equal class has just this. If you're in the equality class, you've got to implement both of these two things. Okay, we actually only have to implement one, but both are defined. Odd odd classes are the ones that are defined with ordinals in. So they implement greater than or equal to, less than or equal to, less than. They also implement max and min. Okay. So integer double implement EQ and ORD, so they have both equality and ordering. And just for class, can you think of a num type that isn't an ORD class? So what's a num type if it's not ordered? Because that's something that can be of num type but isn't an ORD class. Okay, we'll talk to you in class on Wednesday. Thank you.